In this video, we're diving into automated code analysis using the Capa toolset, Binary Ninja plugins, and OALabs HashDB. Now, Capa is one of my favorite automated static analysis tools. I've introduced it in earlier videos, but just in case you're not familiar, Capa is fantastic for identifying interesting capabilities in malware, such as C2 communications, file system interactions, and encoding or encryption mechanisms, just to name a few. I've already downloaded it, and I placed it in my VM here under C Tools Capa, which I'm showing you right now on my desktop. And now what I'd like to do is run Capa against one of the shellcode samples that we discussed earlier in this series and see what we can learn about it. So I have my command prompt right here. I'm now going to go ahead and type the following command to try and learn about the shellcode we extracted from mount.exe. So I'm going to go ahead and type the absolute path here to my capa.exe. I'm also going to use a -r option. The -r option allows us to specify the path to a rule set. So while Capa includes a built-in default rule set, I prefer to download the latest version from GitHub and point Capa to that updated rule set on my system. So in this case, it is going to be at the following location. It's also worth mentioning that by specifying a -r, you can make use of your own custom rules, making it a flexible option for tailoring Capa to specific analysis needs. I'll then go ahead and specify the mount.exe shellcode we extracted earlier and hit enter. Now down here at the bottom is where it specifies the capabilities that it has identified in the shellcode, and it has found some interesting things. For example, we see references to obfuscated stack strings. It's saying that there are 8 matches for that particular rule. We also see references to this shellcode accessing the PEB, the process environment block, which could indicate dynamic API resolution. These findings give us useful leads, but we need to see where exactly they occur in the code to understand the context of these potential capabilities. So to get even more context, we can add the -v option. So let me go ahead and clear my screen here. And then I'll go back to my previous command and add a -v and hit enter once more. So now we have quite a bit more information, and I'll have to scroll up to actually see all of the rule matches. And underneath each rule match, what we're seeing are references to the virtual addresses where the corresponding code actually resides. And just to clarify, all of these addresses assume a base address of hex 690000, and if we scroll back up to the top of the output, it specifies that base address right here. So now that we have these addresses, let's go ahead and pivot into code analysis using Binary Ninja and actually jump to these virtual addresses, at least some of them that have been listed here. Hey everyone, just a brief interruption here. Do you ever struggle to define your malware analysis process or wonder where to keep your notes? You're definitely not alone. A ton of my students bring this up. So I put together a simple template I personally use when analyzing Windows executables. Click the link in the description and I'll send it straight to your inbox. And since it's a Google Doc, you'll always have the latest version. I'm also exploring some new ways to support your malware analysis journey. So let me know what you think and enjoy the rest of the video. So first, I'm going to minimize this command prompt, and I'm going to drag and drop our mount.exe shellcode into Binary Ninja. I'm going to want to specify that base address that was in the Capa output, which is 690000. And as I mentioned earlier, this is a 32-bit Windows code. So we're going to choose Windows x86, and then I'll press open. Let's now take one of the virtual addresses from our Capa output and actually jump to that location within the code. So for example, if I want to take a look at one of these encode data using XOR matches, let's go ahead and grab this address right here. I'll copy that virtual address. I'll go back to Binary Ninja. We do want to take a look at the actual code. So I'll go to linear here, and I'll then do a G, and I'll paste this code and press accept. Now this basically takes us to the basic block where the XOR operation code resides. If I wanted to look at this in disassembly instead of the high-level IL, I could just hit tab, and here we are looking at the disassembly. If I hit spacebar here, I can very clearly see that we are looking at a loop, and of course, if I want to take a look at it in the high-level IL, we can also see that it's represented here as a do-while loop. No matter how we choose to look at this code, what we can see is that we have a 4-byte value right here that is being XORed with the contents of ECX, suggesting some sort of XOR decoding or encoding happening here. To further explore this, we could step through the code in a debugger to see what data is being transformed and how the output looks, but we won't do that for now. That's just a direction we could take our analysis based on this rule match. Now, if I go back to my Capa output here, I could also explore another rule like this one that says access peb LDR data. Let's go ahead and copy this first address right here, go back to Binary Ninja, and I'll again paste that address and hit enter. Here, Binary Ninja does a great job of identifying structures and members related to the PEB or the process environment block. I can see the code accessing the PEB, specifically dereferencing the LDR field. This allows the shellcode to eventually access the in load order module list, which tracks the loaded DLLs. And I won't dive into all of the associated structures and members here, but two important fields I do want to highlight are one, the DLL base, which holds the base address of a module and is a starting point for eventually enumerating all exported functions of a DLL. And I also want to highlight the base DLL name.buffer, which contains the address of the module's name. These are the components required to calculate an API hash, which is a technique often used to dynamically resolve APIs in an obfuscated manner. In fact, you can see up here that this function takes a single argument. And if we look at references to this function, which we can identify down here on the bottom left, I'll just click on the first one. We'll see that in each of the cases where this function is being referenced, which many of them are right here, you see a hexadecimal value being passed as that single argument to the function. These hex values likely represent an API hash derived, again, from hashing the module name and an API name. An API hashing function, which is basically what I'm suggesting this is, takes a hash as an argument and compares it against hashes of different module and API name pairs until it finds a match, allowing the correct API to be resolved and then eventually called. If you're wondering how to translate these hexadecimal values into actual API calls so we can understand what functions are being resolved and executed, just stick with me. We'll get there soon. So by running Capa against this shellcode, we've already identified and confirmed some helpful insights into the shellcode's characteristics and capabilities. And of course, we could spend more time looking at the many other rules that I simply don't have the time to go over here today. But we could jump to each of those virtual addresses and begin understanding at the code level the context of each of these matches. Now I want to highlight an important feature of Capa that can further improve our ability to automatically analyze executable content. In order to further explain this, let's go ahead and just check out the help menu of Capa. So I'm going to open up a new command prompt here, and I'm just going to type capa.exe-h to go ahead and print out helpful information about how we can further take advantage of this tool. If I then scroll up a little bit, I want to highlight the -b option. The -b backend option controls how the target file is processed before Capa applies its rules. For executables, this means selecting a disassembler to handle the binary before Capa analyzes it. Since Capa's results depend on the disassembly process, using different backends can produce different findings. Now, by default, Capa uses Vivisect, but as you can see here in the help menu, there are other options, including, for example, Binary Ninja and IDA Pro. So to illustrate the impact of choosing different backends, let's analyze some shellcode that we first looked at in part 3 of this series when we used floss to extract decoded strings. Now to begin with, I'm just going to run Capa as we have in prior cases just to show you the default output using the default, namely the Vivisect disassembler. So I'm typing that same path to Capa. I'm going to again do the -f for 32-bit shellcode. I'll also specify the path to my rules directory. And the file we're going to look at now is called sc.bin, and I'll hit enter. Now, as you can see down here at the bottom, Capa identified 5 capabilities, but let's see how the results change when we switch to the Binary Ninja backend. Now, before we run Capa using a Binary Ninja backend, there are 3 requirements I want you to keep in mind to actually make this test work. Number 1, you need to install the Capa Python module. So far, we've been using the standalone Capa binary. However, to use the Binary Ninja backend, we need to install Capa as a Python module. The full instructions are in the documentation, but all you really need to do is run the command pip install flare-capa. Number 2, to run Capa with the Binary Ninja backend, you need the commercial version of Binary Ninja. That's because only the commercial version supports headless processing, which Capa relies upon. And the last requirement is installing the Binary Ninja API, which is pretty straightforward. It's just a matter of running an install script. You can find the full instructions again in the documentation, which as always, I will link to in the description. Okay, so now that all of that is behind us and I've taken all of those steps, let's run Capa again, but this time with Binary Ninja using the -b option. In order to make it easy to compare this output with the output I generate using the Binary Ninja backend, I'm going to quickly do a little bit of window reorganizing here. There we go. And now I'm going to type the Capa command. So notice I'm not specifying the full path to Capa, namely c/tools/Capa. That's because I'm now using the Python installed version, which will interact directly with the Binary Ninja backend. And since it was installed via pip, it's automatically available to me in my path. I'll go ahead and hit enter now. As you can see, there are some differences between the command I ran up top here using the default Vivisect disassembler versus the bottom output where I'm using the Binary Ninja backend. Binary Ninja seems to have found two new capabilities here. One is the check for peb being debugged flag, and then the other one is get ntdll base address. And if we look at the above output, the original output, we'll see that Vivisect did identify something that Binary Ninja did not, and that is that it contained obfuscated stack strings, right? We don't see a hit for this particular rule down here below. So just to be clear, running Capa with the Binary Ninja backend isn't always better. I've seen cases where using the Vivisect backend has more rule matches than using the Binary Ninja backend as well. The key takeaway is that different backends offer different perspectives, and running Capa with multiple backends can help uncover a more complete picture of the shellcode's capabilities. You might have noticed that Ghidra isn't listed as one of the available Capa backends. However, in other videos, I've shown how to use Capa's Ghidra integration, which lets you run Capa within Ghidra and easily navigate to the functionality it identifies. If you missed that video, I'll certainly link it in the description. One major benefit of the Ghidra integration is that Capa's output appears directly in the Ghidra interface, allowing you to click on addresses associated with Capa rule matches and jump straight to the relevant code instead of copying and pasting it, which is what we've been doing. Unfortunately, Binary Ninja doesn't currently have a built-in UI plugin for Capa. However, there is a way to import Capa's results, or at least some of them, into Binary Ninja so that you can browse findings a bit more easily within the disassembler. In the Capa GitHub repo, there's a script that allows you to load Capa's results into Binary Ninja called import2bn.py. To demonstrate this script for you, first we need to run Capa and specify the JSON output format so Binary Ninja can actually read the results. Let me go ahead and do a little bit of cleanup here before running this command. So I'm going to take one of the earlier commands I ran against the mount.exe shellcode, and I'm going to remove the -v and instead do a -j to print out the JSON output. There's no need for the -v because the JSON output will contain all of the verbose information. And I'm going to go ahead and output this to Capa _mount_sc.json. Then I'll hit enter. So after we run this command, we can briefly inspect the JSON output, which should be on my desktop right here. I'll just go ahead and double click it to open it up in VS Code. And then I can format it to make it a bit more readable. Let me go ahead and quickly trust this window. Then I can go back here, right click, and choose Format Document. And this is, of course, going to be all the data we want Binary Ninja to process so that it can allow us to more easily browse to some of Capa's findings. Now, since the Binary Ninja import script isn't available currently in the plugin manager, we're going to have to manually install it. The instructions to manually install a plugin are, as always, included in the Binary Ninja online documentation, but let me cover the basics here. First, we're going to need the script, which I do in fact have on my desktop right here. Okay, this is the import2bn.py script. Next, we're going to need to create a folder associated with our new plugin that we want to actually run within Binary Ninja. So to do that, at least the easiest way I think, is within Binary Ninja, we're going to go to Plugins and then Open Plugin Folder. And this is basically where we are going to want to create a folder associated with this plugin that we are trying to manually install. So our next step per the instructions is to go ahead and create a folder associated with our plugin. So I'll call it Capa_Binja. Within here, I will then drag and drop our import2bn script. And because the documentation for manually installing a plugin indicates that the folder associated with our plugin must contain a __init__.py file, I'm just going to go ahead and rename this to init.py and hit enter. And now we need to go back to Binary Ninja and basically restart the application. So first I'm going to save this analysis by going to File, Save, and I'll just save this on the desktop for now. And then I'm going to open up the command palette by doing Command P, and I'm going to search for Restart Binary Ninja and Reopen Files. And I'll hit Enter here. And it has to be restarted Binary Ninja in order to basically reload our plugin. So now once Binary Ninja is reopened, I'll go ahead and browse to our plugin by going to the Plugins menu here and choosing Load Capa File. I'll then go to the desktop and find our JSON output, which is right here, and I'll click Open. And if we keep an eye on the bottom of the screen here in the log, you'll see we have a few interesting statements, which basically represent Capa rules that it is now identifying here in this log output. Now, these are rule matches that you might recall seeing when I ran the Capa command in my command prompt here. If, for example, I click on the RC4PRGA address right here, if I single click on it, it automatically takes me to that address, and it even adds a comment here in the Binary Ninja interface indicating that this function matched a Capa rule. Now you might notice that there are some results definitely missing here. I only have 2 matches at the bottom of the screen, and when I ran it in my command prompt, we saw 5 or 6 in that case. The reason for this difference is that this import script currently only imports Capa matches that apply at the function scope. It does not include matches at the basic block or instruction scope, which means certain low-level findings like obfuscated stack strings or specific instruction-based behaviors won't be referenced in Binary Ninja after importing the JSON file. So just to emphasize, each of the approaches I've discussed using Capa, whether it's running it with the default command line, using different backends, or importing results into Binary Ninja, has its pros and cons. The key is understanding these differences so you can get the most value from your analysis with the time you have. All right, there's one more thing I want to cover in this video. Earlier, when we looked at the mount.exe shellcode, we saw some function calls where a hexadecimal value was passed as an argument. I mentioned that these are API hashes, a common technique used by malware to obfuscate function names. There are several ways to decode these hashes and determine which APIs are actually being called. Number 1, you could debug the code to track which function is resolved at runtime. Number 2, you could do an online search for one of these hexadecimal values, and depending on the hashing algorithm used, you might find blogs and other write-ups with these pre-computed values and the APIs they actually represent. But in this video, I want to demo another Binary Ninja plugin that makes this process easier by leveraging the OALabs HashDB service. This is a growing repository of hashes that malware commonly references to obfuscate function names, registry keys, process names, and other strings. The plugin allows us to look up hashes against this database and resolve them to actual API names. Before we start, keep in mind that this plugin requires an internet connection, so make sure your VM is temporarily connected to the internet. Once connected to the internet, we're going to install the HashDB plugin here by going to Plugins, Manage Plugins, and then I'm going to type HashDB. It's only one hit that you should identify. I'm then going to go ahead on the bottom right here, or the middle right, and click Install. It's going to mention some dependencies here. You can go ahead and click OK to install those as well. And then at the bottom, you'll eventually see a message here saying that a plugin has been loaded. Now let's go back to the code that actually referenced some of those hexadecimal values. Here we go. And just bear with me here. This will be a bit of a multi-step process to take advantage of OALabs HashDB in the context of Binary Ninja. So we're just going to focus first on this hexadecimal value right here. First thing you're going to do is right-click, and you should see HashDB now in the context menu. Now, if you chose hash lookup, essentially it would ask you to specify a particular hashing function. So let's say that we don't know what the hashing function is right now. We would then want to choose hunt. So what I'm suggesting is first, go ahead and choose hunt, unless you've already done in-depth code analysis to identify the hashing function, which we're going to assume has not been done yet. If I choose hunt, it's going to now try and determine the actual hashing algorithm that is implemented here in the code. So now we are presented with the results of this plugin trying to identify the specific hash. And we really have 2 hits here. And one of them references ROR13, which is a very common API hashing algorithm used in malware. So I'm going to go ahead and just choose this one for now and press OK. So we've gone ahead now and chosen the hashing algorithm. Let's now try and resolve the actual function name. What we're going to do now is right click again on this hexadecimal value, go to HashDB, and now choose hash lookup. So it identifies this function as load library A and is asking if we want to import all additional function hashes from kernel32.dll, which is where the code for load library A would reside. I usually click OK because if the code references one function from a module like kernel32.dll, chances are there are going to be more, and this saves us some clicks later. So I'm going to go ahead and press OK. And at first it looks like nothing has happened, but actually the plugin has added an enum entry mapping the numerical hash value to the actual API name. To see the resolve name, we're going to again right click on this hexadecimal value and go to display as, and then choose enum member, or we could just hit M on the keyboard. I'll go ahead and click on this now. Then on the left-hand side, you'll see that load library A is already selected. And on the right-hand side are all of the hashes and their corresponding function names based on importing all function hashes from kernel32.dll. So there's not really anything else to click on here. All you do is press select enum on the bottom right. And now you see the hexadecimal value has been resolved to load library A. And we can then quickly repeat this process for all of these other hexadecimal values. I'm going to hit the keyboard shortcut, M, and then I'll hit Tab to go to select enum and hit Enter. And now we can quickly go through this process for the other hexadecimal values. So I'll hit M on the keyboard now to shortcut this process. I'll then tab over to select enum and hit Enter. Now it says get proc address. I'll arrow down to the next one, hit M again, tab, hit Enter. And as you can see, it's just going ahead and quickly replacing these hexadecimal values with all of the actual APIs. Eventually I get to this scenario, the fifth value, I believe, where pressing M doesn't reveal a valid API. That means this hash wasn't included in the previous import. So to resolve it, what I have to do, let me close this window here, is right click again, go to HashDB, and then do another hash lookup. The results map to NT flush instruction cache here, which is within ntdll.dll. So let me go ahead and press OK to now import all of the associated hashes for this DLL. And once that is complete, I can again hit M here, and I should now see an associated enum. So I'll hit Tab again, and then press Enter. Down one more time, I'll hit M, followed by Tab, and then Enter. And now we've gone ahead and replaced all of those hexadecimal values with meaningful API names. And after resolving these API hashes, I could spend some more time understanding where the API is actually going to be called. For example, I can see the return value of resolving virtual alloc is placed into EAX_2. So if I highlight it as I just did, and then scroll down, I can see right here is where virtual alloc is actually going to be called, and I could continue performing code analysis. So that's a pretty quick walkthrough of how we can use the Binary Ninja HashDB plugin to decode API hashes and figure out which functions this malware is actually trying to call. It's a handy tool that speeds up analysis and certainly helps us make sense of some otherwise obfuscated content. All right, well, that wraps up our look at using Capa for automated static analysis. We ran Capa, we tested different backends, and imported results into Binary Ninja to guide our investigation. If you're enjoying this series, make sure to subscribe so you don't miss what's next, because in part 5, we'll use binary emulation to analyze shellcode dynamically. Thanks for watching, and I'll see you next time.